So welcome to the last lecture. So today we'll continue on and first start with the proof of the fact that an elliptically regular boundary condition B is L2 graphically decomposable. So I hope that we recall that last time we constructed the spaces V plus minus, W plus minus, etc. I won't write them again in the interest of time. But the main point was that we showed, maybe just for the spaces of interest, where'd that go? For the spaces of interest at least, so the thing that I really want is we had this V minus, which was equal to P minus V star minus, which was P minus acting on P minus star of L2 intersected with intersected with the orthogonal complement of W minus star in L2, where, if we remember, W minus star we defined as P plus L2 of the boundary condition. W minus was P minus star of the complementary boundary condition, right? So maybe it was wrong for me to try and write this again because it's a bit complicated. And of course we had the W plus, which was the intersection of simply the boundary condition with the positive, with P plus, right? I mean, these can be more general than the spectral projector. So let me just let's just remind ourselves of these spaces. I won't get into talking about any more of the other spaces because we will show for what we will show, this suffices, right? So all right, so now the proof that we will have today is that B elliptically regular implies B is L2 graphically decomposable. All right. Okay, so we just have to keep in mind the spaces that we defined. So we have already defined spaces V plus minus, W plus minus, etc., satisfying the requirements in the definition, okay, of L2 L2 graphically decomposable, right? So we've already, so that was the content of the first step in all of this. The first proposition was that we constructed these spaces. So what do we need? So today we need a map G V minus to V plus. So this is what we're going to construct, right? So we need so we construct remains to construct, I should say. Of course, it's what we need. Remains to construct G such that it restricts to a bounded projector at the H half level, with the same requirements of G star if we restrict. So this is really the restriction to H half. So the restriction of G star to H half takes us from V plus star a half to V minus star a half, with B equal to the graph of of G restricted to H half plus the W plus, right? So this was the W plus here. Pardon me. So that's what we will prove now. The existence of this G. Okay. So first we'll actually construct the map G restricted to H half. Okay, so the first step is construction of G naught that takes us from V minus a half to V plus a half, and also a H naught that takes us from V plus star a half to V minus star a half. Okay, so for that, let's define a map. Define X minus, which is going to map us from the projector P minus restricted to B minus, let me just see. Why am I writing? No, it's B intersect W plus perp. So it takes us from W plus perp, now it's going to map us to P minus B, right? So of course, yeah. And of course, last time we saw that this space is precisely equal to V minus a half, right? That's what we saw last time. Okay, and similarly, we define a map chi plus star, which takes us from P plus star restricted to B perp H check P plus of D intersect now with W minus star perp. So when I write the perp here, this is in L2, right? So maybe I should explicitly write this here. So this is perp L2. And this maps us from, well, maybe I've moved this across a little bit. Oops, I took W plus with me. This takes us from B annihilated H P plus of D intersect W minus star perp L2, and now it's going to map us to P plus star B perp H hat P plus of D. Okay, so we're going to define such maps, and okay, so that is the map. So it's just the map P minus acting on B intersect W plus perp L2, right? So that is the map X minus. So I should really say I should say X minus dot equal, right? So those are the two maps that we define. And so we show that X minus is a bounded isomorphism with bounded inverse, i.e. it's a Banach space isomorphism. Okay, so and of course a similar conclusion. So I'll talk about the X plus star in a second, because of course a similar conclusion holds for that, but it's the exact same argument that I'm going to give here. Okay, so the first thing I want to show, right, is that sorry, just give me 1 second. I have this injury on my hand and it's interfering when I'm writing, except now oh god, my scissor has gone missing. Oh, it's on the table. Alright, too bad. I just have to stick the Yes. Nested list within a nested list. Okay, so the first thing is that what's going on? X minus is surjective. Okay, so let X be in P minus B. So this is if and only if X is going to be equal to P minus of some B, there exists a B in B. Okay. So now we're gonna cut B up by the orthogonal decomposition of L2 with respect to the space W plus, right? So W plus and W plus perp. Okay. So X is equal to P minus B, which is equal to P minus of what now? This is PW plus perp W plus B plus PW plus W plus perp of B. Okay. However, this second projector lands us in the complementary subspace to the P minus, right? Because W plus by construction is a subspace of P plus of L2. So this projector kills this space. So in the end, we end up with X being equal to P minus of PW plus W plus perp W plus of B. Since W plus is in the kernel of P minus, right, which is equal to P plus of L2. Okay. Also, so we've seen this trick a number of times now. Also, we have that PW plus perp W plus of B is what? So this is equal to, just from this expression itself, this is just equal to B minus PW plus W plus perp of B. So what does that tell us? So this is now in B and this is also in B, right? Because W plus was the intersection, so maybe I wrote it up here. W plus was the intersection of the P plus projector intersect B. So it's also a subspace of B. So this is now in B plus B, which is of course in B. So what does that tell us? So that tells us that X is equal to P minus of P W plus perp W plus of B, where PW plus of perp W plus of B is in B intersect W plus perp, right, as promised. So that's the map that we want. So we have an element in here and we show that there exists an element here which maps to an element in here. Okay, so that's what we've shown. So the second point. The second point is that this is injective. Oops. So why is it injective? So by linearity, it suffices to show, so by linearity of X minus, it suffices to show that the kernel of X minus is 0. Okay? So now let U be in B intersect W plus perp such that X minus of U is 0, right? But X minus of U is equal to P minus of U. So 0 is equal to X minus of U is equal to P minus of U. Which implies that U is in P plus L2 of partial ME. Okay, so that's the conclusion that we want, but U is also in B intersect W plus perp. So now we have that U is in P plus L2 partial ME intersect B intersect W plus perp. But what is this first space? P plus L2 partial M of E intersect B is precisely, that was our space W plus. So so then we get from this that this is W plus intersect W plus perp, but these are now complementary subspaces, right? And because they're complementary subspaces, this is going to be 0. Okay, so the last point now is that X minus is bounded with bounded inverse. So why does this follow? So we have that B intersect W plus perp is closed. We have from last proposition, we have that P minus of B is closed. So in particular, they're Banach spaces with respect to in the H half norm, right? So well, I should say in H half. Both both in H half, and P minus descends to, well, we know that P minus is bounded in H half, right? We know that P minus is bounded H beta partial ME to H beta partial ME bounded. So this is a hypothesis we have on a boundary decomposing projector for B beta in the range minus a half to a half. So in particular, it's true at a half, and therefore chi minus is bounded. So now we have a bounded bijection between Banach spaces, so the open mapping theorem. So now we have a bounded bijection between Banach spaces. So by the open mapping theorem, X minus inverse is bounded. Okay? So similarly, chi plus star is also a bounded map with bounded inverse, and the argument mirrors this, right? Okay, so it's just upon replacing the relevant spaces with the relevant spaces. Okay, so now we come to the second point. So now we write that B is equal to the graph of G naught plus W plus. Okay, so again we have a nested, second nested thing. So the inclusion this way. So clearly W plus by construction is a subspace of the B by construction. So it suffices to prove that the graph is contained in B. Okay? So let V be in V minus a half, which is P minus B. And by A, we let U equal to chi minus inverse of V, which is now going to be in B intersect W plus perp, right? So remember, the map X takes us from B intersect W plus bijectively to P minus of B. So now let's have a look. So now, okay, so the only thing in all of this is that I never defined the map. So that's a bit of a problem. So let me define the map. Oops. Started talking about it, but I never defined it. Okay. So define the map G0 to be equal to PV plus W plus P minus L2. Okay, so we already have a decomposition, so I'm just going to now look at the projector that projects to the V plus space, composed with X minus inverse. Okay, and this is clearly a map now that takes us from V minus a half to V plus a half. And the map H0 we define as PV minus star W minus star plus P plus star L2, composed with the map chi plus star inverse, which now takes us from V plus star a half to V minus star a half. Okay. Okay, let me say, since by previous proposition V minus a half is precisely P minus B, and V plus star a half is P plus star B perp H hat P plus of D intersect. No, that's correct. What am I talking about? That's correct. Yeah. Okay, and by previous proposition, the first one we proved. So step number one, we have that PV plus W plus along this space maps a H a half to H a half. Right, and similarly for the PV minus star. So, okay. All right, now let's get back to it. So we claim that that B is the graph in this way. So we can write the U in this way, and then now let me so now we have an element in B intersect W plus perp. Good. Now let me look at V plus G0 of V. So V plus G0 of V is equal to V plus PV plus W plus along P minus L2 X minus inverse of V. Okay. So what is that? So that's exactly equal to X minus of U plus. So now what do we have? Now we have PV plus W plus P minus L2 of U. Okay, so that's what we have. So now so now the action of the X minus acting on U is exactly as the map P minus, right? So that was by definition, and now I'm going to do this. So V plus W plus P minus L2 of U, and now I'm going to add this piece, W plus V plus P minus L2 of U minus PW plus V plus P minus L2 of U. But remember, V plus and W plus add up to the projector P plus. So that was that was a part of the first proposition we proved. So actually the sum of these two projectors is P plus. So we have P minus of U plus P plus of U minus PW plus V plus P minus L2 of U. But then this adds up to the identity. So we have U minus PW plus V plus P minus L2 of U. Okay. So what? So this is now in, so U is now going to be in B intersect W plus perp. So we have this being in B intersect W plus perp plus W plus, and that's clearly in B. Okay. So, right. So I just want to make a remark here that, so you might look at this and you might be tempted to think that this projector is 0. Okay, projecting to W plus. But this is where, this is an important lesson in why for projectors you have to really care about what it projects along. So of course, if we replace the W plus, the V plus plus P minus L2 with a W plus, then it would certainly be true that this quantity is 0, because remember U is in B intersect W plus perp. However, this projector is no longer projecting along the orthogonal complement to W plus. So it could very well be that it has a piece along this complement in W plus. Okay? But for the purpose of the proof, it doesn't matter anyway. Alright. Now we prove the opposite containment. So let B in B and write B equal to P W plus perp B plus P W plus perp W plus of B. And let's just define this maybe to be B plus B plus perp, just to make the notation easier. So now B plus perp is clearly, right? So from what we said before, because the W plus is a subspace of B, always, by construction. So therefore, this projector PW plus perp along W plus B is going to be B minus this thing. So in particular, this is also going to be in B. And we've seen this before. So what I want to say here is that this is certainly in this intersection. And letting V equal to X minus B plus of perp, which is now in P minus of B, okay? What do we have? So we have B plus perp is equal to X minus inverse of V by definition. So I should say letting V be this. So this is what? So this is equal to, now I'm going to split along, I'm going to split along the projectors P minus and the P plus, right? So I'm going to take P minus of chi minus inverse, inverse V plus. Now I'm going to split the positive projector now into V plus and the W plus. So I have V plus W plus P minus L2 of chi minus inverse of V, and now I have PW plus V plus P minus L2 chi minus inverse of V. Okay, but what is this? So the first quantity, alright, so the first quantity here P minus chi minus inverse of V is what? So P minus, so chi sorry, I keep calling it chi. X is equal to the projector P. Restricted to this subspace, it's restricted to this subspace B intersect W plus perp. So the P minus and the X minus inverse, they cancel. So we get V here. Plus, what is this second object here? This is the definition of the map G naught. So this is G naught of V. Plus, now we get some term here. So rewriting this out in terms of the B plus, we get some term here, PW plus V plus P minus L2 of U. Okay, so, sorry, not of U, B plus perp. So again, the point, I want to just make the remark that this projector might not necessarily be zero, right? For the reasons that I said, that so note, so this is a side remark, so side remark, PW plus V plus P minus L2B per plus is not necessarily zero, even though B plus perp is in W plus perp, since this projection is not along W plus perp. Okay, so this is why doing these things, you should always explicitly, with painstaking detail, without making any assumptions, write out everything in terms of the projectors and make the projectors work, right? If you can make it work with the projectors, you can do it, but it's very easy to go wrong at this stage if you try and if you try and do this just intuitively, because it's well, it depends on what kind of intuition you have, of course. So we only have actually that W plus perp is isomorphic. So here, I mean, the one of the difficulties of this decomposition is really that we need equalities, not just isomorphisms, right? We really need the spaces to equal things, and that's much harder to organize than isomorphisms, of course. All right, so with that side remark, so now however, the point is that we still win because PW plus V plus P minus L2B plus perp is an element of W plus, which is of course contained in B. So that shows that B plus perp is in graph G naught plus W plus. Okay? And so then we get that B equal to B plus B plus perp, which is in W plus graph G naught W plus, which is clearly contained in graph G naught plus W plus. Okay? So maybe yeah. Okay. Maybe I'll just leave it. Think about why graph G naught intersect W plus is empty, right? Okay. Similarly, we get that B annihilated H check P plus D is actually equal to the graph of H naught plus W minus star by mimicking this argument. Okay. Alright, so now we have to get to the map G somehow, right? So we promised to map G, which is an L2 bounded map. So let G, so now for the map G, for the map, so now we construct G V minus to V plus such that G restricted to H half is equal to G naught, and G adjoint restricted to H half is equal to H naught, right? So H naught is also a map that maps at the level of H half regularity, right? So, okay. So for that, let's let G naught star be now the map that takes me from V plus star in to a minus a half. So now this adjoint is with respect to the pairing of V minus a half and V minus star minus a half, right? So remember we had, let me just say, recall V minus plus a half V minus plus minus star minus a half is a perfect pairing extended by the L2 pairing, right? So we've already seen this in a previous lemma. So now I want this to be the adjoint map at the level of H minus a half. So this maps from V star minus a half to V minus star minus a half. And we show that G naught star restricted to H half is actually equal to minus, sorry, this should be minus H naught. Okay. All right. So fix now a U in V plus star to a half, and a V in V minus a half. Okay. We note that these spaces annihilate each other, right? So this is equal to V minus star V plus is equal to B perp H P plus D. These are all equal to 0. Okay, these all annihilate each other by definition. So what do we get? So we get that 0 is now equal to V plus so we're just calculating now the inner product. So V plus G naught V, U plus H naught U. So what's this equal to? So because of this condition here, this is precisely now going to be equal to G naught V U plus V H naught of U. So that tells us that we get V G naught star of U. So remember, this is at the level of the H minus a half object, is equal to V minus H naught of U for all V in V minus a half. But by previous proposition, V minus a half is dense in V minus and V minus negative a half. So we get that G star naught of U is equal to minus H naught of U. Okay, so at least this shows us that this map G naught star, when we restrict to H half, is actually a H half bounded map. Okay, so so maybe I jumped the gun a bit here. So what I wanted to show actually was this, right? So let's kill this for the moment. So what I really wanted to show here was actually not that. Copy. Actually, what I wanted to show was this. Okay. Now, oops, went to the wrong next page. All right. Let's see. So now in D, we have what? We have this. So construct a G such that G restricted is equal to this G naught. Okay. Maybe actually I'll rephrase that. I should say G naught extends to a G V minus to V plus bounded, such that G extended means exactly that. This, right? Okay. So how do we do this? So here we need to, so what do we have so far, right? So what we have so far, we have this map G naught at the level of H half, and then we have its adjoint at the level of H minus a half. And we know that that map restricted to H half agrees with the map H naught that we've constructed, right? Using the adjoint boundary condition, or at least a pullback of the adjoint boundary condition. So the point now is that we want to obtain G. So there's not so many ways in obtaining the G. So ideally we'd like to obtain the G through interpolation. So in order to do that, we need to know that we can interpolate these spaces V plus minus to get what we want. Okay, so we do this by interpolation. Okay, so we already have that the L2 spaces interpolate nicely. Okay, so this interpolates along H half and H minus a half. Complex interpolation at the midpoint gives us L2. We also know that the projectors PV plus minus, well, this is somewhat cumbersome to write it in this way. What do I want of these spaces? Well, I should maybe say, well, I'll say, it's not the same plus minus as the plus minus here, so I have no option but to write it separately, I think. Plus P minus plus H a half is going to map me from H half ME to H half ME, and we now have the same thing but with minus. Okay, so now what we want to do is we want to use this retraction co-retraction theorem. So we have to, so recall that for, so we use retraction co-retraction theorem. And for that we have to have a retraction R from boundedly from b1 plus b2 to some spaces b1 tilde plus b2 tilde. So these spaces are interpolation couples, which means that they embed into a larger space. And S, which is the retraction to the the co-retraction to the retraction, which takes us from b1 plus b2 tilde to b1 plus b2, restricting to retractions, and so restricting to retractions, co-retractions on bi, so boundedly from bi to bi tilde and bi tilde to bi respectively. So recall that what it meant for it to be a retraction was what? It was that RS, so RS is the identity, right? That's what it meant for it to be a retraction and co-retraction. Okay, so anyway, that we don't need to use this so much because we're dealing with projectors. So let's make some choices for our spaces. So B1 is going to be H half. B2 is going to be equal to H minus a half. So of course they're an interpolation couple with the choice B3 being H minus a half, right? And B1 tilde, I want it to be equal to V plus minus, so for either choice, a half, and B2 tilde is going to be V plus minus negative a half, okay? And now I'm going to set the retraction R to be equal to PV plus minus I'm just going to use minus a half here because it restricts to a bounded projector on H half, right? So W plus P minus plus H minus a half. Okay, that's going to be my retraction, and my co-retraction, I just want it to be the identity. So why is this okay? So actually maybe this is SR. Can't remember if it's RS or SR. So I wanted to go from B to here. Yes, it's and S takes me from here to here. So R takes me from here to here. Yes, that's the correct order. So why can I just choose S to be the identity? Well, you see, my choice of spaces are the ranges of the projector itself. So on the range of the projector, the projector just acts as the identity. So so that's why I can make this choice. So the retraction co-retraction theorem then gives me this. Retraction co-retraction theorem then gives me that V plus minus, so it says that S theta, V plus minus, so what I have is, because it's the identity, so half V plus minus minus a half, so this is equal to, so this is at theta, this is S theta, V plus minus a half, V plus minus minus a half, it says is equal to the retraction at theta acting on the larger spaces. So now we have this being PV plus minus minus a half, W plus plus P minus plus H minus a half, theta acting on H half, partial ME H minus a half, partial ME at theta equal, okay, it's just at theta. By choosing theta equal to a half, right? Because if we choose theta equal to a half, then we know that this is L2, and this trajectory is also just a projection to L2. And to the L2 spaces, right? So the projection to V plus minus. So then we get precisely that this is equal to V plus minus is equal to V plus minus a half, V plus minus minus a half. Okay, at theta equal to a half. So in fact, I mean, of course, we could do this to any of the spaces. We could choose the parameter theta in a different way, and because my W plus is always containing H a half, my projectors P plus minus map boundedly for H beta back into H beta, for beta between minus a half and a half. I would always have this projector actually projects to the V beta space, and so this would in fact, by choosing theta differently, we would be able to get a similar conclusion for all of the spaces in between, right? We'd be able, so it's saying that the spaces P plus the V plus minus interpolate in a nice way. Okay, so now now that we have that, by a similar argument to before, we get that H naught adjoint. So H naught is now a map that is H half bounded, right? This maps V minus a half to V plus, sorry, V minus minus a half, V plus minus a half, extending G naught. In fact, we could just get it from what we proved before. So we proved that G naught star is equal to H naught, so then H naught star has to, extending minus G naught, right? So it has to now be, the adjoint of the adjoint gives us back the correct object. And therefore, so what do we have? We have that H naught star takes us V minus a half to V plus a half, minus a half, and we have H naught star restricted to a H half is V minus a half to V, because this is equal to minus G naught, this is equal to V plus a half. So by interpolation, obtain G, which is equal to the map where we interpolate between these two, right? So H star naught at theta equal to a half, which, because we've shown at the scale half the spaces are V minus, this is taking us from V minus to V plus boundedly, right? And also it extends this map G naught by construction, okay? And extends G naught by construction. Okay, and with that we can scrub that off and say that that is the theorem, right? So we've supplied, so the restriction of G to H a half is precisely equal to H naught, as we showed before, right? It is now a map that's L2 bounded, that on restriction restricts to a bounded map in H half on these relevant spaces, and we have that its adjoint restricted to H half is equal to the H naught, which is also a map that maps boundedly between H half. So that proves the elliptic decomposition. So you see, it's quite intricate that we have to really play with both of these, with the boundary condition and its annihilator simultaneously, and have all of the spaces matching up in a perfect way in order for all of this to work. So the history of this theorem really is due to Baer and Ballman. And there, of course, this number of spaces they had was half of what we have here. Because there they were looking at a self-adjoint adapted boundary operator A. And in that case, one can one only obtains decompositions which are orthogonal. So, for instance, the V minus star spaces will be exactly equal to the V minus space, etc. So the number of spaces is a half, and so this is an extended argument that now really allows us to deal with general boundary decomposing projectors. Okay, so that's the end of that. So to end the topic, let me just return to talking about some boundary conditions. Okay, so let's return to boundary conditions. Because now we have these theorems, let's look at some boundary conditions. So one of the interesting things that happens with boundary conditions, just also so I can relate many of these things to the classical theory. So let's start with the definition. So we say that a boundary condition is S plus a half semi-regular B, so which is elliptically, so so this is the definition of, so we say, wrong order, we say an elliptically regular B is S plus a half semi-regular if there exists a P plus that's boundary decomposing such that the W plus is in HS partial ME. Okay, so here S is, so we should say for S greater than a half, right? S greater than or equal to a half. I mean, we always have that an elliptic boundary condition is one regular because we have always, with respect to a boundary decomposing projector, that W plus is in H half. So this is only relevant for greater than that. And G of V minus of S maps us into G of V plus of S. For B graphically decomposed with respect to P plus. So it is S plus a half regular if this also holds for B adjoint, right? So if it's semi regular for B dagger also. Okay, I don't want to, and I don't have the time to really get into pseudo-differential projectors, but let me just mention it because it has to be mentioned for the sake of relating all of this to the classical theory. So let P be a classical pseudo differential projector of order 0. So a classical pseudo-differential projector, so this is one, i.e. One that can be written locally as an integral against a symbol uh, via the Fourier transform. So it's local, so we can exploit the Fourier transform where the symbol has an asymptotic expansion. So that's the classic nature of it, right? This asymptotic expansion is the classic nature of it. But I don't want to get into it. I'm going to brush this under the carpet, but I just want to, define some boundary conditions now. So traditionally, boundary conditions were more or less constrained, and notions of ellipticity were constrained to just the pseudo differential projector world, right? But we've already seen in the proof of the relative index theorem that this is insufficient. We really need to go beyond the pseudo differential operator world in order to get the full class of these elliptically regular boundary conditions. And the matching condition, as we saw, is one where we cannot write this as a range of such a projector, right? Okay, so the definition now. So the definition. So P is a classical pseudo projector of order 0. Then we define B equal to the projection of a H1/2, and then we take its closure in H check. Okay, so is called, so maybe I'll put BP, pseudo local boundary condition. Okay, and if now we have E prime in E restricted to the boundary, a smooth subbundle, then BE defined, so this is defined as P acting on, H1/2 acting on M, landing us in E, taking the closure in the check space, is a local boundary condition. Okay, so one nice thing you can maybe even read off directly from what I've just written is that if we have a local boundary condition, and if you multiply by a compactly supported smooth function up to the boundary, then we remain in that boundary condition. So if you take a u from the element, if you take a u which is in the domain of the operator corresponding to a local boundary condition, and you multiply it by a smooth cutoff to localize near the boundary, then we end up back in the boundary condition. So chi times u is back again in the domain of the operator. But that's not necessarily going to be true for a pseudo-local boundary condition, right? So if you choose a spectral projector, there's no telling that we're actually going to end up back in the spectral subspace. So local boundary conditions are very nice, but let me also remark, every local BC is pseudo-local. Okay, so the existence of this smooth subbundle means that we have a projector, fiber-wise projector, and that will give us a pseudo-differential projector of order 0. So now let me give you the important theorem in all of this. Unfortunately, we will not prove it. So B P is equal to P H1/2, so I'll just say is a pseudo-local boundary condition. then the following are equivalent. So 1, BP is elliptically regular, and in that case, actually, we don't need to take the closure. It's just P acting on H half ME is good, i.e. P H half ME automatically closed in H hat of D. Okay? 2. So now we're going to return back to the world of projectors. The reason I'm giving this at the level of, of the spectral projectors, of course we could phrase this with respect to the general boundary decomposing projectors, but we won't do that. So for some and equivalently all invertible adapted boundary ops A, P minus chi plus of A mapping L2 to L2 is elliptic or equivalently Fredholm. Okay? And then we have a condition, a local condition that we can check. So for all psi in the cotangent bundle, x star partial m non-zero, no, this is P, this is P subtract. So we have a pseudo differential projector P, and we subtract P and the chi minus, the chi plus of A. So x is in the boundary, and we have this object here, EX, so from the fiber EX to EX, principal no, that's separate. So at this level, at L2, this on a closed, because we're on a closed manifold, an operator being elliptic is equivalent to it being Fredholm. So maybe I'll put equivalently Fredholm. The sum all is separate, right? Okay, so the principal symbol of the projector restricts to an isomorphism . Yes, the sum all means if there is one, then it's true for all. Okay, the principal symbol restricts to an isomorphism from the real negative parts of the spectrum of I sigma A x psi lambda to p x psi e x, and p star x psi restricts to an iso from the real negative parts spectrum of the eigenspaces of I lambda A adjoint xi lambda to p star xi ex. Okay, it's a bit of a hefty statement, but anyway, these are important. If you continue to think about these things, you will come across words like Lopatinsky Shapiro, etc. So these are all related to that. In fact, all the Shapiro-Lopatinsky-Shapiro boundary conditions are all fit into this theory, right? All of this generalizes that. But I won't ponder upon that much longer. So the corollary that I want to leave us with here is that every pseudo-local boundary condition is pseudo-local elliptically regular boundary condition is infinitely regular in the language we just phrased. In particular, if, so I should say pseudo-local elliptic boundary condition, well, I've put B prime. So in particular, if dBp of V is smooth up to the boundary as an interior object, then V is actually smooth up to the boundary as a section, i.e. smooth up to boundary. So this is very important when trying to look at regularity of eigensections up to the boundary and so on and so forth if we're on a compact manifold. Okay, so let's actually examine. So we've in the majority of this talk we've actually talked about I mean, even the APS boundary condition is a pseudo-local elliptically regular boundary condition, okay? So we've seen plenty of them, but up to boundary. So we've seen a lot of pseudo-local boundary conditions, but we've hardly seen any local boundary conditions, right? So very early on, I gave an example of the Dirichlet and Neumann, but that was for a second-order operator. So what are some local boundary conditions for first-order operators? Examples. Local BCs. So first, let's let MG be Riemannian. And let's take the normal vector inward pointing normal and the tau to be the conormal of that. And EF is now going to be my complexified so it's going to be the differential forms we're taking complex values. So this is T star of M, so maybe I'll put the C here, twisted by C. Okay, well, it looks like a plus. All right, and my operator D is now DH, which is D plus D star. So we have, so because, so at the boundary, we have that the P forms at the boundary, star C, M, or I'll take the C, restricted to the boundary, we can actually write as P forms of, what's going on, star, okay, I should maybe have x's here, x partial M, plus now I have tau x wedge the P minus 1 forms at x partial M, okay? And we have that, so we have that phi now breaks up into phi something in here plus tau x wedge phi, which I'll write as perp, right? So it's to denote tangential and orthogonal. Okay, so the E prime now, I'm got. In the second, well, that's wedge the P minus 1 forms. Right? Okay, so the E prime I'm going to now set to partial M, which is going to be, why did I put a star here? Okay. This is partial M plus, twisted by C. And then the absolute boundary conditions. So the B absolute boundary so these are called the absolute boundary conditions, is H half taking values in E prime. And what is this? This is exactly equal to U in H half ME, such that the normal part is 0. Okay? So these are called the absolute boundary conditions. Okay. And E double prime, similarly, I'm going to set to tau wedge C partial M. And then the so-called relative boundary conditions are where we take H half partial M E double prime, which is U in H half ME, such that the tangential component is now 0. It is a relative, so-called relative boundary conditions. Okay, so these are these are two local boundary conditions for the Hodge-Dirac operator. Now, lastly, so let's now instead assume that this is not just Riemannian, but spin. And D slash is spin Dirac. And E equals F is the spin bundle. So so now we define, let G be a map, taking us from the restriction of M to the bundle to the boundary, be a boundary chirality operator. So that satisfies that the square is the identity, that it is an isometry. So this is the spin connection, of course, right? That it's parallel. That it's when it composes with the spin Dirac operator, it anti-commutes at the symbol level. Sorry, at the symbols level. D x psi for all psi in T star x partial M, and it commutes with the tau, i.e. the conormal, right? X tau composed with G dx. So there's such an operator is called a boundary chirality operator, and there we get subspaces, which is equal to the eigenspaces of G, the plus minus. So it has only two eigenspaces because it squares to the identity, and so we have that the spin bundle is now equal to E plus plus E minus. Okay, and the B plus minus, say H half partial M E plus minus, are local elliptically regular boundary conditions. Okay, so so we've already seen this object in even dimension. So when dimension of M is even, and we take G equal to the complexified volume form acting on the spinors, complexified volume element acting on the spinors through the representation, of course, through representation gives rise to the spaces that we've already seen before, right? This splitting into the plus minus eigenspaces of the spin bundle. But now let's consider the case when M is odd. When M is odd, we can set G equal to I tau as the chirality operator. And actually, so the boundary condition, say B plus, is called the MIT bag condition. Okay? And actually this was originally conceived to model putting electrons in a bag. Okay, so finally this justifies the image here. Well, for some reason it doesn't point to the right thing, but it justifies the image that we've been carrying along this this entire course. And so this is the MIT bag condition, right? This is a local boundary condition that somehow is meant to represent putting these electrons in a bag. Okay, and with that we will end the course. I have really nothing more to say. Thank you for coming along for the ride. It's been really great. A lot of wonderful things have come out of this course. So thank you for your attention.